Sometimes we talk about the independent variable and dependent variable in terms of causation. So we kind of talk about the independent variable being a measure of cause, and the dependent variable being a measure of effect. And so if you look at the previous example on the modern scientific method, treatment as the independent variable, the measure of treatment was one group or the other. You assume the two different groups had two different kinds of treatment. And that would be the independent variable. The dependent variable would be the IQ measure after the treatment. Now, the other characteristic of that traditional scientific model is that the independent variable is categorical. They're in one group or the other. And the dependent variable is continuous. It's on a scale. And that's the traditional, typical pattern for the modern scientific method. It's also the reason that, just as an aside, it's the reason that the social sciences in the latter stages of the 19th century, early 20th century, felt the need to develop all these instruments. And so we developed IQ instruments, we developed personality instruments, we developed, efficacy, we developed self-satisfaction, we developed all these instruments in the social sciences. The rationale, the reason is we wanted a way to try to create continuous data for dependent outcomes. And so we wanted to make this thing that we called IQ, which we still don't know what it is or what it ever was. We want to make this thing IQ something that is on a continuous scale. We want to make this thing of self-efficacy on a continuous scale. We want to make this thing of types of personalities on a continuous scale. And so the big boom in instrument construction at the beginning of the 20th century was primarily an attempt by the social sciences to create data that would allow them to manipulate and analyze data in the modern scientific method model. And, that obviously led to some good fits. It obviously led to some lousy fits. And so that kind of spurred the need for a new type of analysis, and that's why we kind of picked up on a qualitative methodology, because it was a different way of looking at things. But anyhow, we go back to that basic question we had off the modern scientific model. When is the difference a difference? Is 5 points in that scenario a difference? Or is it purely random? Is it just a random fluctuation in the data? And so we have to go back and look at just a little bit of early statistical modeling, early statistical theory. And this is based on the basic statistical analysis PowerPoint that you have up on As You Learn. And so let me go back to that for a second. And so this is the basic there we go. This is kind of where we started, and we're talking about looking at continuous data now. We're talking about looking at data that's on some sort of interval-based scale. And so let's say this was a group. This was a group, and these measures, these scores represent some measure, whatever that measure is. Maybe it's number of pounds, lost in a month or whatever. And so we know that there's two types of descriptors to a continuous data set. There are descriptors that talk about central tendencies. The only one of those that's actually terribly meaningful is the mean. And that's just the arithmetic average, but it's a characteristic that continuous data sets have. The other characteristic that continuous data sets have is what's called deviation. And deviation, in most cases, is simply the random error component that's in measurement. And so we've got, these 5 scores, and they're different from each other. Well, part of the reason they're different is sort of our rationale is that difference, that deviation from the mean, is part of the random characteristic of these scores. And so we assume this to be random. When we, because of various computational reasons, mainly we've got negatives and positives that cancel each other, we end up having to square those things simply to be able to give us something to manipulate. And when we square those things, we end up with what's called a sum of squares. And since we know that sum of squares is affected by sample size and is not a relative term from sample to sample, we have to take sum of squares and we have to make it something that would be relative from sample to sample. And so we take a mean of the sum of squares, except that we don't do by n, we do by n minus 1, and that's simply because we have, anytime that you look at a theoretical data set, we know that the last member of that data set can't vary, and that's just a theoretical construct. And so when we're getting means and things like that out of samples, we always do n minus 1. So when we take that sum of squares, square deviations to be exact, and we find the mean of that, we get what we descriptively could call the average squared deviation, but we have a term for that. We call it the variance. Variance represents the squared random error, or theoretically the squared random error within a group of numbers, continuous numbers. But we got, we squared it up to get there, so we got to get rid of the square, so we take a square root, and the square root is what we call standard deviation. Now, because of where it came from, because it came from deviation, which we assume to be the random error in any group, standard deviation now becomes our standard error term, or to use a statistical terminology, our unbiased estimate of random error within that group. Our unbiased estimate of random error within that group. Now, we kind of lose some of the language, and so it becomes just an unbiased estimate of error, or an unbiased estimator. You'll see terminology used different in different places. And so that 5.52 there represents what we would call random error. Now, if you begin to think about that, and we'll talk about its distribution here in a minute, but if you begin to think about that, what we're always wanting to get at is random error versus systemic or biased error. And so almost all statistical tests involve a ratio, which is some statistic, Z, T, A for different things. But that ratio, that statistic, we'll just call it a stat, is equal to observed error compared to random error. That random error we express by what we call an unbiased estimate. And so we have a ratio. We have what we actually see compared to what we'd expect to see purely by random, if nothing else was going on. And we have an unbiased estimate of that random that comes from standard deviation, because standard deviation is calculated from random error. Now, one of the first functions, statistical functions that we arrive at, or statistical concepts we arrive at, is what's called a z-score, or sometimes called a standard score. And that standard score is simply the difference between a particular value, let's say whatever it is, X in a data set, minus the mean of the data set, divided by standard deviation. And so we have the difference between an actual number and the mean of the data set it comes from, divided by standard deviation. And this gives us what's called a z-score or a standard score. Z-scores and standard scores have some really interesting characteristics in terms of distributions. And if you look at the description here, subtract the mean from the raw score and divide the result by the standard deviation, just the formula I just showed you. And so here's an example of standard scores or z-scores. Let me get something up here that we can look at. And so if I start with a particular score, 18, in a set of data that has a mean of 12 and a standard deviation of 5.52, this data set we were just playing with, the score minus the mean is 6 divided by 5.52, which gives us a z-score or a standard score of 1.09. And so if I do the same calculations for the other 4 members, I get 0.910 because 1's at the mean. So obviously the score minus the mean is 0, so it's going to turn out to be 0. A minus 0.91 and minus 1.09. Now notice these are symmetrical. And z-scores or standard scores tend to be symmetrical, which makes sense because you would expect some to fall below the mean, some to fall above the mean. They'll not always turn out to be perfectly symmetrical, but they will be symmetrical more often than not, or relatively symmetrical more often than not. But the interesting characteristics of these things is that when you do a distribution of standard scores, let me get that garbage off of there. When you do a distribution of these standard scores by z-score or standard deviation, you have a distribution that looks like this. And so if you go back and think about the characteristics of this, the actual raw value would be 12 at the mean, the raw score, and the standard deviation was what, 5.52. So it would be 17.52, one standard deviation unit up, and 23, two standard deviation units up. If you went down the other way, it's 12 minus 5.52, so it's 6.5 as a mean value, as a raw value. If you go down further, it's 1. Now, those values are by z-score, converted to raw score. Now, some other characteristics of the standard normal distribution is that the density, or the distribution in between z-score lines, will always be the same. There will always be about 34% of the cases between the mean and one standard deviation unit up. About 13.5% of the cases are percent of the space. It's actually a measure of space between 1 and 2. And so if you sum some of that up, then you're always going to have about 47.5%, give or take, of the space, the density of the curve, between 0 and -2 standard deviation, and between 0 and +2 standard deviation. And so when you add those up, what that tells us is that 95% of the area, 95% of the density lies between 2 standard deviation units down and 2 standard deviation units up. Now, the beauty of the standard normal distribution, of a distribution of z-scores, is that the density in those different segments is always exactly the same. Doesn't matter what the original data set looked like. The density between 0 and 1, or 0 and -1, is always going to be the same. And the density between 1 and 2 is always going to be the same. Now, as you can see, 95% of the density, or 95% of the cases, lies between 2 standard deviation units above, 2 standard deviation units below. That 95% should mean something to you. In terms of hypothesis testing, we're saying that our null hypothesis would be that scores most likely lie within the middle 95%. That there's no difference between any scores in this middle 95%. They're all subject to what we'd expect to see by random variation. If we come outside of the 95%, we get into the 2.5 here and the 2.5 on the other end. Those represent unusual scores. And so we would be rejecting the null and saying that a value that's out here or out here would be a significant outlier from the group. And because we know the density in here, we can talk in terms of likelihood. And so there's a 95% chance that most scores will be in this middle, and there's only a 5% chance they'll be on the outside past -2 or past 2. And so scores in those areas we would call unique, or to use the statistical terminology, we would call them significant. And so we know the logic that gets us here. But it's also the basic logic that gets us through all the other statistics. In that we have an unbiased estimate of error we have some comparative or observed outcome, so we can create a ratio. We know what that distribution looks like. It won't be like standard normal at anything less than infinity, but we know what it looks like. And so we can predict what are called critical values beyond which on the curve are outliers that we could call significant outcomes. And so the one logic set, the one thought logic process that works with standard normal distribution and works with z-scores works across the board with all the other statistical analysis regimens that we use. We just have to have that unbiased estimate of error of what random error would look like, and then we have to know what the distribution of that particular ratio would look like. Questions? Okay. Excuse me a moment. Hey, I'm doing this without pain meds too, so. Okay. All right. Now, those are only working with individual raw scores. Standard scores only works with individual raw scores. But what if you don't have that? What if you have sample means? Well, if you go back and think about, if you remember the little bunnies and dragons thing about the central limits theorem and normality, one of the things that was in that particular little video was the fact that sample means are also normally distributed. And any measure of sample means, differences between sample means are normally distributed. But what you have to have is all possible sample means of a given size from a set of numbers. So I want to give you the simplest case scenario of that. Go back to this basic stats piece. Let's assume that we have this theoretical population that only has 5 people in it, 5 subjects in it. I know that's an extreme, but we're not doing anything here that's not, we're not creating any special scenarios. Let's just say we have a population that has 5 people in it or 5 subjects in it. And these measures, 87654, represents some score for those individuals. And let's say we want to pick a sample mean, a sample size of 2. So I need to know all unique samples, size 2, that I can draw from this population of 5. And so I go through and pick those samples. I have 8 and 7, 8 and 6, 8 and 5, 8 and 4, 7 and 6, 7 and 5, 7 and 4, 6 and 5, 6 and 4, and 5 and 4. So those represent every unique sample, size 2, from this population of 5. There are no other possible combinations. And so if we get a sample mean for each one of those samples, 8 and 7, sample mean is 7.5. 8 and 6, sample means 7. On down through 5 and 4, sample means 4.5. So I have this set of sample means: 7.5, 7, 6.5, 6, 6.5, 6, 5.5, 5.5, 5, and 4.5. If I look at those, but first, there's a couple of characteristics here. Let me get rid of the garbage. Okay. And so we have population mean. If we look at the population, 87654, 5 members in it, the mean is 6. Sample means 7.5, 7, 6.5, 6, so on and forth, divided by 10. There are 10 samples, possible samples, and that mean is 6. So we know that the population mean is equal to the sample mean, the mean of all possible samples of a given size. So the mean of the population is the same as the mean of all sample means. Now, because this is a special case, the only special case this is size-wise. This is actually representative of the general case. It's just a little bit more easy to find samples size 2 unique out of a set of 5 than it would be to find all the unique sample size 20 out of a set of 10,000. I mean, we could calculate it and figure out how many that would be, but obviously it'd be very difficult to pull all those possible samples. And so this is a case that's basically smallest possible case, but it would apply to all cases. If we distribute those sample means, it begins to look like this. And just with those 10 means, we begin to get a normal distribution, or at least it begins to look like a normal distribution. As it turns out, sample means are normally distributed. Now, it's not a standard normal distribution. The normal distribution varies according to sample size. So you'll get one set of sample means, or you get one distribution for sample means of for say an N of 10. You'll get another distribution for an N of 20. By the time you get to about 30, somewhere between 30 and 50, you don't get much change as you go forward. It just looks a little bit more normal, a little bit more normal, a little bit more normal. And so if you get to infinity, sample an infinite number of sample means, it will be, once again, a perfect normal distribution. But since we know what these distributions look like, we can know what the actual values of particular statistics, what's the likelihood of a particular value occurring. And so it's just like z-scores, we can know when we've met that 95% threshold or less than 5% threshold. And so this is a sample distribution of sample means. Now, the history of this, which I mentioned, I think the last time we met, has a sort of an interesting history to it, in that the Dr. Carl Pearson, who basically developed this statistical test, he was teaching doctoral courses in psychology in the early 20th century in Switzerland and France and a few other places. And he was an American college professor for a while, but anyhow, Pearson decided he needed to develop a tool for his students to be able to answer that question. You know, when is a difference a real difference, as opposed to a random difference? And so he developed this tool, and he called it Students T-Test. And it was so effective, and his colleagues and his peers thought it was such a wonderful notion. They wanted him to publish it, and so he published it in the most exclusive statistical or mathematical journal of the time. I think it was Mathematica or something like that. And he didn't want to put his name on it because he didn't want to be known as a statistician or mathematician. He wanted to be known as a psychologist. And so he called his pseudonym for the piece was called Student's Teacher. And so it became to be known as the Student's T-Test, or eventually became to be known as the T-Test. And so if you'll keep in mind what the z-score looked like, the error term for sample means calculated in a similar way as standard deviation, with obviously some alteration to it a little bit. But the estimate of sample means is called the standard error of the mean, or the SEM, standard error of the mean. And so one particular kind of t-test, one that was developed, Pearson developed to do the modern scientific method, where there were two groups, a control group and an experimental group, had the mean for one group minus the mean for a second group divided by standard error of the mean. And that generated a t-statistic, and it was called a independent t-test because you had two groups. And it generated a t-statistic which had a distribution and somewhere along that distribution were critical values, critical t-values that defined the area that was 95% in the middle and 2.5% on each side. And so if a particular t-value fell out here someplace, it was considered to be a significant difference between the two groups. If the t-value fell in here someplace, then it was considered to be not significant. Now, there are two other t-tests, or two other scenarios. One's called the Part2, and that's for pre-post scores. So if you have a group of subjects and you have a pre-test or a pre-score, and then you do something, or there's a treatment or a period of time passes, and then there's a post-test, post-score. The unbiased estimate term, error term, is called the standard error of difference, SED. It's computed similarly to standard deviation and standard error. Obviously, it come out, you get a slightly different take on things because you're dealing with differences between individual scores, pre and post. And that paired T looks like pre-mean minus post-mean divided by standard error of difference. Just like the other t-test, it comes about on a distribution, fairly normal distribution. There are critical values for paired t's that define the difference between the 95% in the middle and 5% on the outside. So anything that's on the outside of the middle 95% is considered to be significant. So there would be a significant difference from pre to post. Anything that's in the middle 95% is considered to be not significant. So that would give you would accept the null there, the null hypothesis being that there's no difference from pre to post. And there's one last T. And the scenario there is when you have one set of scores, one sample. So it's called a one sample T. And your unbiased estimate of error, random error, once again, is the standard error of the mean, SEM. You do have one additional piece of information, though. You have some population mean value. Now that could be a average score within a school, standard score on some medical test. What's the mean? What's the average normal score nationally? And so that one sample T is the mean of the one group, of the sample group, minus what's called mu, which is just a representation of population mean, divided by standard error of the mean. Once again, you get a normal distribution, and there are critical values at 95% that define the mid 95%, and those critical values determine whether you have significant t-value outcome or not. And that's the first set of hypothesis testing, and the first set of statistics we'll look at. So, questions, comments? Okay. I'm going to do one more video, not tonight. No, not tonight. I need to find some Advil or something. But I will do it, what is today? Wednesday. I'll do it in the next couple of days. And so that we can look at, certainly before the weekend, I can run through an example, a live example of taking that data set that I provided you walking through the analysis and the outcome in JASP. And I'll also put up a forum board for questions you have. And sometime between now and the 9th, probably can't be the 2nd, but probably sometime next week, I'll set up a couple of spots where I can answer questions as you kind of, work through some of that stuff. And I'll post some times and things like that. But I will do a video, walking you through the JASP, and I'll take the JASP file that I generate doing that and put that up also along with the video.
Is that related to, I saw that there's some stuff you updated on the As You Learn page, and there's something that's due October 9th. You were talking about the eval.
Yeah.
Okay.
It includes the descriptive stuff and t-test. I have to double check. I don't think we do anything more than descriptive and t-test on that. And then, but I'll do a video, a sample of the, running the t-test and things like that, so you can have something to look at. And then I'll give you once again the outcome, the output from that analysis, that JASP.
Okay.
And give you the forum board. Y'all are medical people. What am I supposed to do with broken ribs? I mean, we haven't figured out, two things we haven't figured out. What the hell to do with a cold and what to do with broken ribs. We need to work on that. And I've had both of those in the last 2 weeks. So I guess I'll survive. But anyhow, yeah, so I'll do that video, exemplar, and put that file up. And by sometime early next week, I'll put up a couple of times. If you have some questions, or I'll be live in case you have something you want to ask. Kind of work through, or you can email me or whatever, but I'll create a couple of live spots in there somewhere. Would a live spot during the day work for anyone? Probably not. Okay, I didn't think so, but I don't sleep, so I could do one at 2 o'clock in the morning, but I'm pretty sure y'all wouldn't like that. But we'll do a couple of evenings. We'll get a couple of time slots there that we can. I'll be here, and if you have questions or whatever, I'll answer all those. If nobody shows up, I'll just turn it off and take a pill and go to sleep. Any questions, comments, other things? All right, folks, I will run these recordings tonight, get them up on YouTube with the links, and work on the other video piece. Check the evaluation to make sure that we're covering everything we need for it. And then I'll have that video up certainly by sometime later in the weekend. I don't know. Won't be too long. Okay. All right. Have a good evening. Hang in there.
Thank you.